like I said, this whole unit is focused on the solar system. Today specifically, we're going to be talking about the moon and eclipses. So first off, let's talk about moon formation. The general consensus among scientists is that the moon was formed via what's called the giant impact theory, where the basic idea of it is during the early solar system, there was a lot of like protoplanets. And scientists believe that a protoplanet about the size of Mars crashed into Earth during the early solar system. And during that crash, a lot of like rock and dust and metal were emitted back into space. And that kind of vaporized or molten rock kind of cooled and condensed into what formed our moon today. The biggest amount of support for this theory is the fact that rocks from the moon that we've analyzed have a very similar composition to those from the Earth. So it seems very likely that Earth and the moon have like kind of the same source material that they were made of. All right, now we're going to talk about some properties of the moon. We're going to start with albedo. Albedo is a term that just means it's a measure of reflectivity. So it can tell us how reflective a material is. So if something has an albedo of 1, it is a perfectly reflecting surface. It'll reflect all light that is shined on it. However, if something has an albedo of 0, that means it's a perfectly absorbing surface. So it's going to absorb all the light that hits it and not reflect any back into space. If you look, they've got the albedos for Venus, Mercury, and the moon listed. Venus has a fairly high albedo of 0.65, but both the moon and Mercury have relatively low albedos of 0.11. And here we can kind of see that illustrated in these photos. These are not to scale for size, but they can give us an idea of albedo. The surface of the moon and Mercury look very similar. Venus is way brighter though, and that's because of what their surfaces are made of. So the moon and Mercury have very similar albedos because they have the same type of surface. They both have this kind of dark, dry, rocky surface. Venus, on the other hand, we don't actually see the solid surface of Venus when we look at it. We see its thick white atmosphere. So Venus is completely covered in a very thick atmosphere of whitish clouds, and so it reflects a lot more light. Whereas the moon and Mercury have like dull, rocky surfaces, they're not going to reflect nearly as much. Yes?
So a black hole would have an albedo of 0.
Right, I mean like, yeah, because it's not going to reflect anything, it's going to absorb everything. Fun fact, black holes are a really bizarre object, especially when you think about it in terms of space-time, because they're like an infinitely deep hole in the fabric of space-time. And that's why nothing can escape from them. That's just an aside note. Now, that brings about the question when we're talking about albedo. Well, if the moon's albedo is so low, why is it the brightest object in our night sky? And that's simply because it's the closest. The moon is way closer to Earth than any other celestial body. In fact, it's only about, 240,000 miles away, which is about the same as the width of 30 Earths. Way closer than anything else, and that's what makes it the brightest. we're going to talk about this idea of brightness again when we talk about stars. Because again, what we perceive as brightness, how bright something looks to us, isn't necessarily tied to like how much light it reflects or how much light it emits if it's a star. A lot of it has to do with distance. Also, the moon's distance from Earth tends to vary throughout its orbit because, like the orbits of the planets, the moon's orbit is an ellipse. So it's not a perfect circle, it's kind of like that oval ellipse shape. And when the moon is closest to Earth in its orbit, we call that perigee. And when it's farthest from Earth in its orbit, we call that apogee. They have the same root words as perihelion and aphelion. When a planet is closest to the sun, perihelion, and farthest away, aphelion. It's just saying aphelion means furthest away from the sun. Apogee is meaning furthest away from the Earth. So let's talk about synchronous rotation. You might have heard the idea that the moon is tidally locked with the Earth, or that only one side of the moon ever faces Earth. And that is correct because of synchronous rotation. Synchronous rotation basically means that the revolution period of the moon is equal to its rotation period. So what that means is that the time it takes the moon to rotate once on its axis is the same as the time it takes the moon to revolve once around the Earth. And so because of that, we only ever end up seeing one side of the moon. And I have a short video that I'll pull up here in a second that kind of really illustrates that for us well. Because the video is going to show us, what the moon would look like if it didn't rotate at all, what a quickly rotating moon would look like, and then it'll show us what the synchronous rotation of the moon actually looks like. All right, let's check out that video. So again, first it's showing us what the moon would do if it didn't rotate at all. So if the moon doesn't rotate, we still end up seeing all sides of it just because of the way it goes around the Earth. Now this is the moon with rotation, and this is a rotation period that is shorter than revolution. And with this, you can see that we would still see all sides of the moon if it rotated faster than it revolved around the Earth. But again, that's not what it actually does. Its rotation period is exactly equal to the time it takes to revolve around the Earth. And so because of that, only one side of the moon is ever facing the Earth. All right, let's talk about some other things related to the moon. One of the most beautiful things that's super easy to observe actually is the lunar halo. And a lunar halo is when you get this glowing ring of light around the moon. It's most spectacular when it's around a full moon. And the reason that this happens is that like thin wispy clouds in the upper atmosphere are typically filled with tiny ice crystals. And when moonlight passes through those ice crystals, it's refracted or bent at an angle of about 22 degrees, and it ends up getting bent in all directions, so you get this lovely halo of light around the moon. Sometimes you'll even be able to see like the colors of light separating in the spectrum, so it'll be like a little bit of a rainbow halo. I've found that I see these most often in the wintertime when the air is really cold and dry. But they're really pretty to see, especially if it's a full moon. Next up is what we call the harvest moon. And the harvest moon is just the name given to the full moon that occurs nearest to the autumnal equinox. So whatever full moon occurs closest to the fall equinox, it's called a harvest moon. And a lot of times people will say that the harvest moon appears brighter or a little bit bigger than normal. And that is, due to slight effects that change with the tilt of the Earth up with regards to the atmospheres. Also, as you can see in this image, a lot of times the moon sometimes appears like this kind of like orangey, yellowy color, typically when it's close to the horizon. And that has to do with light being scattered as it passes through the thicker atmosphere near the horizon. It's the same kind of effect that gives us like the colors in a sunset. The light tends to get scattered by the atmosphere, and the one color of light that's scattered the least is red light. And so that typically what gets filtered through and what gives the moon kind of that orangish, yellowy hue to it. A blue moon, we use this saying a lot. You say once in a blue moon, you mean something that happens rarely or very infrequently. When we're talking about astronomy, a blue moon refers to the second full moon in a calendar month. Now, this doesn't happen very often, but it can happen because full moons are separated by 29 days. But most months are 30 to 31 days. So you can technically squeeze 2 full moons within a month. And this happens every 2.5 years or so, we get a blue moon. The moon illusion is another thing that is actually really interesting to do. And you guys can kind of test this actually on your own. All you need is a penny. So when you see the moon right near the horizon as it's rising or setting, it will usually look huge. But if you let it get higher in the sky, it ends up making the moon look smaller. So the moon looks really big on the horizon, but it looks a lot smaller in the sky. The size of the moon doesn't actually change though, and you can test this by holding out a penny at arm's length and comparing it to the size of the moon on the horizon and the size of the moon up higher in the sky. And you'll find that compared to the penny, the size of the moon doesn't change. Now, the reason we perceive it as being so much larger on the horizon is because the human brain is designed to judge the size of things in comparison to other things. So when the moon's on the horizon, it's close to trees and buildings and lots of other things like that. So we can see that, oh yeah, compared to those things, the moon is huge. But once the moon's high up in the sky, there's not really anything left for our brains to compare it to. And so our brains perceive it as being smaller. So it's just kind of one of those fun optical illusions. Now we're going to talk about phases of the moon. So the reason that we have moon phases is because as the moon goes around the Earth, one half of it's always facing the sun. So half of the moon's always lit by the sun, half of it's in shadow, just like the Earth, right? Half of it's always lit by the sun, half of it's in shadow. Our perspective with the shaded and lit half of the moon changes as the moon goes around the Earth. So how much of the lit and unlit side of the moon we see from Earth depends on where the moon is relative to us in its orbit. And so we're going to talk about those moon phases. And we can actually kind of see how this works in the moon phase interactive here. So I'm going to rotate the person on the Earth so that it's nighttime. Right here, here is the moon, okay? The left half of it is lit up by the sun because the sun's on the left in this diagram. The right half is shaded. At this point, the shaded half of the moon is facing Earth. So at this point in its orbit, we don't see the moon. This is what we experience as a new moon. If I drag it about a quarter of the way in its rotation, now you'll see, okay, from our perspective, we can see half of the moon lit and half of the moon in shadow. And in this case, it's the right half of the moon that we see lit up. That's what we call the first quarter moon. So when the right half of the moon is illuminated, it's the first quarter. It's called the first quarter because the moon has made 1/4 of its rotation around the Earth. Then if we take it halfway around its rotation, now we can see at this point in its orbit, only the lit half of the moon is facing Earth. And so this is what we experience as the full moon, when we only see the lit half of the moon facing us. And if we take it to 3/4 of its way around, well now, again, we can see half of the moon lit and half of it in shadow, but because it's on the opposite side of its rotation, which side of the moon is lit and which is in shadow is reversed. Now it's the left side of the moon that is illuminated from our perspective. And this is called the last quarter moon because it's 3/4 of the way around its orbit. All right, so here's kind of our different terms that we use to describe moon phases. First, waxing. If a moon is waxing, that means there is an increase in the moon's illumination. So the moon, the illuminated side of the moon appears to get bigger and bigger when it's waxing. Waning is the opposite. Waning is when there is a decrease in the illumination of the moon. So the part of the moon that's illuminated appears to get smaller and smaller when it's waning. A crescent moon is any moon that is less than half illuminated. So a crescent moon can have a variety of sizes. It's just anything that is less than half illuminated. On the other hand, a gibbous moon is anytime the moon is more than half illuminated. So again, the size of a gibbous moon can vary a little bit, but anything that's more than half illuminated is a gibbous moon. Of course, the new moon is when the moon is between Earth and the sun and we cannot see it at all because only the shaded part, half of the moon, is facing the Earth. The first quarter moon is when the moon has made 1/4 of its way through its orbit, and it is the right half of the moon that is illuminated. So first quarter, right half. A full moon is when the moon is halfway through its orbit, and we see the entire moon illuminated. Again, because the illuminated half of the moon is what is facing us. And the last quarter moon, which is sometimes called the third quarter moon, is when the moon is 3/4 of its way through its orbit. And in the third quarter or last quarter moon, you're going to see the left half of the moon illuminated. So last quarter, left half. That's kind of the big thing to help you remember this. Last quarter means left half of the moon. And so I think these numbers are just kind of in your notes, but this tells us basically the timeline for a full moon phase cycle. So day 0 of the moon phase cycle is considered the new moon. And then it'll be a waxing crescent from day 0 until day 7.5. Day 7.5 is when you get your first quarter moon. And then again, it will continue increasing in its illumination. It'll be a waxing gibbous moon from days 7.5 to day 15. Day 15, halfway through the 30-day cycle, is when you get the full moon. After the full moon, the moon's illumination will start to decrease, and you'll have a waning gibbous moon from day 15 to 22.5. Day 22.5 is the last quarter moon, where the left half of the moon is illuminated. And then it'll continue to decrease towards the new moon from day 22.5 to day 30. So to get through a full cycle of moon phases is 30 days. Now, this is different than actually the period of revolution for the moon. It takes 30 days for the moon to go through all of its phases, but it only takes 28 days for the moon to revolve around the Earth. Which begs the question, why are the lunar phases longer than lunar revolution? And the simple answer is that the Earth is also moving. So the Earth is not stationary during all of the moon's revolution. The Earth is also moving around the sun and rotating on its axis. And so because the Earth is also moving, you get this slight difference in the time it takes for lunar phases, which is just how we on Earth perceive what the moon looks like, versus how long it actually takes for the moon to revolve around the Earth. So now we're going to make this little diagram. We're going to fill in the pictures of the moon phases and label what days they occur on. And we're going to start with day 0 right here. Remember, day 0 is the new moon. So we should completely shade this in for the new moon. So there's our new moon all shaded in. Then the moon's illumination will slowly increase as we have a waxing crescent. And that takes place from day 0 to day 7.5. And again, remember, it's the right half of the moon that's illuminated first. So most of the left half of the moon should be shaded in. Then at day 7.5, we get our first quarter moon. So that means the entire right half of the moon is illuminated. Left half should be shaded in. And then the moon's illumination will continue to increase from day 7.5 to day 15. We're going to have our waxing gibbous. So we should have more than half of the moon illuminated. It's still the right half that is illuminated. Then on day 15, we get the full moon. So we don't have to shade anything in on the full moon because it is completely illuminated. And then from day 15 to 22.5, the moon's illumination is slowly shrinking. That's our waning gibbous. And this is where it switches to being the left half of the left side of the moon that is illuminated. On exactly day 22 and a half, we get our last or third quarter moon. And so the left half of the moon is illuminated. And then the illumination of the moon gets smaller and smaller from day 22 and a half to day 30, and that's our waning crescent. Are we good with the diagram? All right, I will erase it and then we will continue on to where we're going to talk about eclipses, which is actually one of my favorite things to talk about. So let's start by talking about solar eclipses. So a solar eclipse occurs when the moon passes between the sun and the earth, and it casts a shadow on the earth. Now, anytime you have an eclipse, there's two types of shadows associated with the eclipse. There is a dark inner shadow, which is called the umbra, and then there is a lighter outer shadow that's called the penumbra. And you're only going to see a total eclipse if you are within the umbra, the dark inner shadow. And I really like this diagram because it really illustrates what a small shadow the moon casts on the earth. And this is really the big reason why it's really hard to view a solar eclipse. It's not necessarily that solar eclipses are rare. They occur with pretty regular frequency. However, the umbra shadow of the moon on the earth is very small. So you have to be in a very specific location in order to view a total solar eclipse. And another unfortunate thing is most of the earth is water, the ocean. So a lot of times solar eclipses occur just over the ocean and they don't occur over land, which makes it even more difficult to try to observe them. Now there's three main types of solar eclipse. The first is the total solar eclipse. And this is where the sun is completely blocked by the umbra shadow of the moon. At that point where the sun is completely blocked, we call totality. And you can see an example of this in our first image here. And the cool thing about being able to observe totality is that because the sun is completely blocked, you can actually look at the sun during totality without any kind of protection on your eyes, but only during totality. The moment totality starts to end, you cannot look at the sun anymore. A partial solar eclipse occurs when the penumbra shadow, that lighter outer shadow of the moon, falls on the earth. And the penumbra shadow only partially blocks the sun. And so we can see an example of this right here in the middle. It was a partial solar eclipse that you would have been able to view from here in Michigan back in August of 2017. And I'll show you a couple of pictures that I snapped during that when I observed it. There's also a third type of solar eclipse called an annular solar eclipse. And an annular solar eclipse only occurs when the moon is at apogee. So when the moon is farthest away from Earth in its orbit, and it appears slightly smaller. At that point of apogee, the moon's shadow is not quite big enough to completely block the sun. So when you have an eclipse where the moon is at apogee, it's an annular eclipse because there's this thin ring of the sun still visible even when the shadow is completely over the sun. Because the moon's far enough away, that shadow is just not quite big enough to totally block the sun. So back in August of 2017, this is the last time you could have viewed a solar eclipse from North America. Unfortunately, I was not able to travel to the path of totality, so I observed the partial solar eclipse here in Michigan. And here's some pictures of my pinhole projector that I used to observe the sun because I didn't have any fancy glasses. And then this is an image that was taken of the sun at totality during that time. And if you ever get the chance to observe a total solar eclipse, it's highly recommended that you do so. It's a very interesting and unique experience. Fortunately, there is another total solar eclipse not passing through Michigan, but it's gonna get close. So in October 14th of 2023, we're gonna experience an annular solar eclipse, so not a total solar eclipse. There will still be a ring visible around the sun, and that's gonna be visible from the western United States. But in April 8th of 2024, we're gonna get another chance at a total solar eclipse. And the path of the totality for this total solar eclipse is going to come as close to us as northern Ohio and Indiana, which is not nearly as far as you would have had to travel in 2017. In 2017, I think you had to go as far south as Tennessee or Kentucky. But personally, I plan to make that happen because I would love to see totality. At any rate, there will still be a partial solar eclipse that you'll be able to view here from Michigan. So now let's talk about lunar eclipses. In a lunar eclipse, you have kind of the different geometry. Instead of the moon being between the sun and the earth, now the earth is between the sun and the moon. And you get a total lunar eclipse when a full moon is completely covered by Earth's umbra. So again, the dark inner shadow. So you still have the dark inner shadow of the umbra and the lighter outer shadow of the penumbra during a lunar eclipse. During a lunar eclipse though, unlike the sun, the moon isn't completely blocked out. Instead, the moon is really heavily shaded, and it takes on kind of this blood red color, which is really very beautiful. You'll get a partial lunar eclipse when a full moon is partially covered by Earth's umbra. So if the full moon is kind of right here instead of completely in the umbra, that's when you get a partial lunar eclipse. And then the third type of lunar eclipse is called a penumbral eclipse. And that is when the moon is completely within the penumbra shadow of the Earth. So it'd be right here. Now, penumbral eclipses are really only interesting to scientists typically because the amount of darkening that occurs on the moon during a penumbral eclipse is so incredibly slight that most people will not even notice a difference. And I'll show you a picture of that. So here on the left, this is the moon, just normal, no eclipse going on. This right here is a penumbral eclipse. The difference is so slight that I feel like I wouldn't notice, personally. I'd have to be looking at the moon a lot more often than I am now to notice the difference. Now, a total lunar eclipse is a totally different ball game. It is very beautiful, very noticeable. The moon takes on this kind of blood red or rusty color, and it's absolutely fantastic. In fact, because of that color, full lunar eclipses are often called blood moons too. Now, again, while we're going to be able to view a partial lunar eclipse on May 26th, we won't be able to view the total one because the moon will be below the horizon for us when it is totally during the total eclipse. The next time we here in Michigan will be able to view a total lunar eclipse is going to be May 15th or 16th of 2022. So during that time, the moon will be above the horizon for the entire eclipse, and we will be able to view all of it. Last thing that we kind of want to wrap up with is a lot of times, especially when we show like the flat diagrams that we normally do for solar and lunar eclipses, it kind of makes it look like, well, why don't we have an eclipse every single month when the moon's between the sun and the earth and the earth's between the sun and the moon? And the reason for that is that the moon doesn't orbit the earth in a flat plane. So like if this is the plane that the earth is in, the moon orbits at an angle to it. At an angle of about like 5 degrees, I believe. Yeah, 5 degrees. So a lot of times, even though the moon is between the sun and the earth, it is above the plane of the earth. So its shadow just kind of passes above or below the earth. And that's why eclipses don't occur every month. It's because the moon's orbit is actually tilted with respect to Earth. And that wraps up everything that we're going to talk about with regards to the moon and eclipses today.